Hi, welcome to the Signal Pad. I have another product review for you guys, and it's the Tektronix TSG4106A. This is a new synthesizer and vector modulator from Tektronix, and this particular model goes all the way up to 6 GHz. This is a really cool unit because it's extremely compact, and this is very important. If you've ever been in a lab environment and you have a synthesizer that you want to lug around, those things are quite heavy and quite wide and can be quite cumbersome. But this vector modulator plus all of its features, it really fits into the size of what a typical DMM for example, would be on your bench. So this is a really big plus from its size dimensions, and its performance is really good, as we shall see during the experiment. So I'm interested in taking it apart and seeing exactly how it's built inside and doing a bunch of experiments and putting it through some tough tests and see how it performs. So let's get started. And just a quick reminder to make sure to check the Tektronix website for a full specification of this unit, because every parameter you might be interested in is already listed there. Now there's no point for me to go through the specification because you can easily look it up yourself. I'm more interested in testing the unit and pushing its performance limitations in some of the experiments, which would be much more interesting. But everything including, which would be very useful, a full phase noise plot of the behavior of the unit is listed. For instance, you can see it has quite a good phase noise. At 10 kHz offset, we are at 1 kHz offset, we are below -100 at the 1 GHz output. You're sitting at about -90 dBc per hertz at 100 Hz offset, which is quite good. So you make sure you take a look. It's a very, very stable unit, and once I take it apart, you will see why. And all the other parameters are fully listed here, so make sure you check it out. So let's go ahead and take a look and see what's inside the unit. I just took the rubber sleeves off, and I have to tell you, the mechanical engineer who's designed this has had a lot of fun because there are so many screws. I mean, there are screws stitched all around this unit, and that means that I had to take 30 screws off just to take the top panel off. And it looks pretty cool, actually. It's unfortunate that the plastic covers, the rubber covers, block it, but let me see if I can get this off. There you go. Should be easy now. There we are, and ta-da! And wow, look at that! I didn't expect that. We have a Stanford Research Systems crystal, well, an oscillator, 10 MHz reference, and it's a high stability, low phase noise 10 MHz oscillator. And you can see that this is part number SC10. I've seen one of these before. These are fantastic, by the way. I'll tell you a little bit about them. This is grade J, and I think if I remember correctly, there are multiple grades. You know what? I have the PDF. Let me grab that to refresh my memory. And indeed, there are different grades of this. I just looked it up. And grade J, K, and A is the best, and J is the lowest one. Not that they're that different, actually. I'll tell you a little bit about grade J. So the aging of this per day is 1 × 10⁻⁹, and the Allen variance over a 1 second period is 1 × 10⁻11. And the Allen variance obviously is mostly concerned with the noise of the oscillator, actually. Its phase noise at a 10 Hz offset is -120 dBc per hertz, which is extraordinary. And at 10 kHz, we're looking at -158 dBc per hertz. Now, if you jump to grade A, then those numbers, the aging becomes 2 × 10⁻10, the Allen variance becomes 2 × 10⁻12, and the phase noise at a 10 Hz offset becomes 10 dB better, -130 dBc per hertz. But the rest of the phase noise is unaffected. These are double Alvanized oscillators, so they're very stable, as those numbers certainly show. One of the other things that's cool about this is that its harmonic distortion is very good. It has a 60 dBc harmonic distortion, which is amazing, and that means the tone is really, really pure, and it doesn't produce anything else except the 10 MHz, which is great. These things are must be fairly expensive. I actually don't know how much they cost, but they at least have to be $400 or $500, or maybe $300 or $400. And very, very cool. And obviously they're tunable to some extent because you can calibrate and correct for that. And some of these numbers mean, I think the first number over there means the slope under which the tuning is done. And it's great to see one of these in here. It's going to lead to a fantastic performance, as we shall see. So now, obviously, this has to be disassembled further for us to see something. But the other thing to note is this power supply. It's fully shielded. There's a fan on this side of it, which likely blows air out of the unit. And looks good, so that sucks air from around here, and then probably cools the other things too, although you don't really want to cool this one very much. And you can see over here there is a block that's containing all the RF sections, because the output is right over here. Both the LF and the high frequency outputs are from there. So this block is all of our RF components. And I see some boards here from my angle. I cannot examine it very carefully. There's a connector over there. So I think in order for us to see a little better, we might want to take some of these components off. Just looking at this, it looks grade A. I mean, it's beautiful. It looks very nicely designed. Tons of mechanical engineering gone into this in order to get into this form factor, and I really like that. So let's go and take a couple of these off so we can take a look. Let me zoom this a little bit maybe so you can see, oops, what I'm looking at. Yeah, so it looks like we might have to take at least a power supply and this off so we can see what's going on. This board that you see here that's elevated, obviously connected to all the back connectors at the back that I just spoke about. So we should be able to take a closer look. So let's take a look at some of these things one step at a time. Here's the Stanford Research Oscillator out of its socket, and look how nice the design is. They have a connector here that directly plugs onto the board. So this is a very modular standalone unit. Interestingly enough, the power for this particular oscillator comes from the front panel, which is interesting, and this is most likely because the front panel can turn the power on and off if needed. I'm not sure why they take it from the front, but I know that the computer is in the front, and we will take a look at that. So very nice. And there's another connector here which is not populated, and I assume that is either for a different crystal or maybe even a rubidium standard, but either way, very, very nice. I really like that. And I have also taken the power supply out, and check it out. I mean, it's fantastic. There's only one connector. Again, just like the crystal, it plugs right onto the board and feeds from these connectors directly into the power supply. So it's just everything just like Lego pieces come out, and it's wonderful. So I'm also going to take the top cover of this because I'm curious to see what's inside it. We can take a quick look at that before moving on. And here's our power supply with the top off, and you can see the main lines coming over here. Proper earth connection to the chassis, which is great. I see multiple transistors and voltage regulators from this portion of the circuit using the body as a heatsink. There's another internal heatsink here which has our different switching transistors directly on it. High voltage power supplies, really nicely isolated, properly isolated. Everything here is glued together. Very compact design. All the capacitors are 105 degrees Celsius rated. The fan is over here. Lots of protection, thermistors and MOVs and so on. There's some adjustments over there. There's a potentiometer there that would allow you to adjust, make some adjustments, I guess. And there's a little LED inside it, but I'm not going to obviously touch any of that. Overall, very, very nice design. Again, compact, clean, and it looks like it might be designed directly by Tektronix. I don't see any other logo. It doesn't look like a generic one. It looks very custom made, and especially with the connector at the bottom, obviously they have custom designed these things to mate with each other. Very happy with that. So let's move on to the main unit. And here's a look from above on the main board, and look at how beautiful and how clean it is. This is really a wonderfully designed piece of instrument. And you can see over here that at the very back where the BNC connectors come in, we have multiple board interfaces which are stacked with a vertical board connecting all of them to the main motherboard. There's also another cable over here which is a sync function. All the synchronized functionality that can be taken from one of the BNCs come from this cable, and all the other signals directly from the motherboard. So it's really clean and straightforward what's going on over there. We have our main power supply connection and the main oven controlled crystal oscillator, the 10 megahertz one. There's a chip FMNI here, which is the GPIB controller. There's another IC here, which is likely the Ethernet controller and some of the other functionalities over there. I haven't taken the label off of it, but it doesn't have much functionality based on its location and the proximity to the Ethernet. Now, what about everything else? Well, if you look at carefully, one of the very first thing that stands out are these 4 different crystals. These 4 different crystals span a very interesting range of frequencies. We have 20 megahertz, 19.6617 megahertz, and this crystal over here has even more digits. This one is 19.607843 megahertz, and in fact, because of the additional accuracy, that particular crystal was underneath this shield, because they don't want that frequency of that crystal to be pulled away by the different interferences that are present within here. So that's how much they have to be careful because of the extra accuracy that a particular crystal is rated for. So now, what are these actually doing? Well, if I were to guess, I think that they're using the differences in the frequencies between these crystals in some way to generate even finer steps resolution in frequency. So they're perhaps doing interpolations between them and some type of computation between them, most likely in analog, in order to get very fine resolution. Remember, this thing can do 1 microhertz frequency steps, and in order to get that, maybe that's what they're doing with these 4. That's my guess, and if you have another idea, I'd love to hear it, but this would be my first instinct about that. The rest of it is fairly straightforward. The 10 megahertz reference is used to lock this Vectron 100 megahertz VCO, which is also a really, really clean VCO, and that's going to drive this chip. And this is a DDS from Analog Devices, AD9852. That's a 300 mega sample per second DDS, and it has some interesting functionalities. It can do AM modulation, PM modulation, BPSK, chirps, and so on, which means that it is likely that those particular types of modulation are actually driven directly, taken directly from this DDS, and that signal is then passed on to the RF block, then mixed with the actual RF signal, and then comes to the output. That would be my guess what this guy is doing over here. Now if you continue over there, we see another large component here. This is an SMC DCSO 1000. This is a 1 gigahertz VCO, and in fact its phase noise is so good that they are saying that it is a SAW replacement, which is quite a big statement, which means they have a very, very good phase noise for that. And this 1 gigahertz oscillator over here, locked to the main 10 megahertz reference, is going to be the fundamental RF frequency of the whole unit, and then it's either multiplied or even locked again in order to reach all the way to 6 gigahertz. Normally they multiply and filter these and then amplify and filter and so on. Now if you move over here, we can clearly see that this portion is obviously responsible for all the baseband generation. Underneath this cable over here, we have a Xilinx Spartan FPGA, and that Spartan FPGA interfaces with the flash memory that is over here, as well as these DACs. These DACs are actually the DAC 5672A. They're from Texas Instruments, 14-bit, 275 megahertz. Each of them is a dual DAC. And this chip over here is another DDS, and this one is an AD9910, which is a 1 gigahertz 14-bit DDS. And this is likely going to generate the clock necessary for these DACs. Now these DACs each have two outputs. Now one of them is clearly dedicated for the IQ modulation, for the single sideband capability of this unit, and this is more than capable to be able to do the 6 megasymbols per second required for the complex IQ modulation that this thing can do. And the other one of its output is likely taken to the LF output, the low frequency output from the front panel, and that is directly synthesized with the DAC. Again, that would be my guess. The other output, I'm not 100% sure what they're doing with the other one, but they're obviously using it for something, because you can see the 4 parallel channels over here. But very cool. I wonder where that one's going. And if you continue looking around, another really cool and interesting thing to see is this interface board. They have designed an interface board with a whole bunch of differential and single-ended microstrip transmission lines on it, which takes signals directly onto the RF block. And those particular signals carry interesting things like the I plus, I minus, Q plus, Q minus for the IQ modulator going in and out of it. As well as the RF blanking, the baseband output comes out of here, the different RF attenuators, the detector for a 4 gigahertz signal. So it means that there is somewhere a 4 gigahertz signal being generated internally, and there's a detector on it, and that is used for ALC purposes and to make sure that this system is working and the signal is present, and so on and on, and adjust the attenuators. And that's how they get feedback from the system to know, to make sure that ALC is actually active and running. And it's very cool. You can see the individual transmission lines. There are some power again going in and out, well, I should say mostly going in. And another thing that you see is a mystery SMA connector here. It looks like it's terminating to 50 ohms. I wonder what that is. Now it could be that that's the coherent output, which would be great, and if it is, I'm pretty surprised that they haven't taken that out, because having a coherent output before the IQ modulator, before the mixers, could be very handy. In fact, it would be if you were testing down converters, for example. But it could be that, for example, this is a calibration pad that they inject their own signal and goes through there and comes out of there, and that's how they can read out what parameters they should use for the calibration. Maybe that's what it is, but either way, it would be very cool. Maybe we can take a look at it just out of curiosity. Let me see, what else did I want to talk about? I think that would pretty much cover all the interesting things. Now in the front panel over here is where the main processor is that drives the LCD screen and all the other functionality. It's right behind there. This is, like I said, this is similar to the Keithley SMU units. Although these signals coming over here are likely from the keyboard, and that is seems to be processed by the FPGA. Other than that, it's beautiful. I mean, it's so modular, it's so clean. Obviously a lot of thought and effort has gone into putting it together with all the different high quality components. I mean, some of the best components you can get for something at this price is very, very nice. So now let's put it back together. And I know you guys want to see what's inside here and open it and take a look at it. I do too, but I'm a little bit concerned about, I don't want to disturb its power calibration. I want to do some of the measurements first, and maybe we can come back to it and take it apart later. But before we go through the trouble, I want to actually measure it and make sure it works properly and do the review on the experiments that I have planned for it. Maybe we can come back to it. But nonetheless, I'm very eager to test it out. So let's take a look at the front panel of the Tektronix TSG41068. This is obviously the 6 GHz model, and you can see a very familiar front panel. If you've ever used the Keithley 2280S power supply series, you'll recognize the LCD screen and the placement of the soft power buttons. It uses the same computer that is used in that power supply. Unfortunately, it doesn't have the touchscreen used in the SMUs and the DMMs from Keithley, which I really like to use, but it seems to work quite well nonetheless. Now on the left bottom here, you obviously find the Type N connector, which is the industry standard for instruments below 26.5 GHz, and you can see that it has a reverse power protection of 25 dBm and 30 volt DC, so it's AC coupled, which is also standard. Right above it, we have a BNC connector for the low frequency output, also matched to 50 ohm, and you can tolerate plus or minus 5 volts, which is great. It looks like that this is recessed into the plastic of the cover. In fact, it is, and at first I was worried that this would interfere with the BNC connectors, but I tried a whole bunch of different ones and they all fit quite nicely, and it poses no problem at all. Now the RF on and off button, which also lights up, is right above here, which is a great place to put it. You don't want it on this side because you want to have the association of the connectors being enabled and disabled with this button. So this is a very good place to put it. And also the power button is recessed into the soft power button, which also works really well. So I like the way they have done that. Obviously soft power buttons here at the bottom, which will be contextually sensitive depending on what's shown on the GUI at the time. And you have a little tiny panel of buttons here for the numbers, and the units are obviously right next to them. And then you have the major component of parameters you want to adjust: frequency, amplitude, and modulation. So really straightforward. The modulation button, enable and disable, also lights up, so you know that you have enabled the modulation by looking at the instrument, which is great. And then you have settings and preset. This feels really nice. It's the same one again used as in the power supply, and it's of course pressable, and you got two little direction arrows. I'm really happy with the layout. It works really well, and it's important because this is such a small unit, and this is one of the main advantages. I mean, you have a full 6 GHz vector modulator with all the functionalities built into it in something that has a footprint of a bench multimeter, which is fantastic. I really like that. And there is also a USB connector in the front used for, you know, saving data, restoring data, updating the firmware, which I just did actually. And otherwise it looks really cool. So let's take a look at the back of it. And the back of the unit, you find exactly what you would expect. Obviously the power over there, and you can see all the holes designated for the power supply ventilation. And there's an IEEE 488 GPIB connector there, which, you know, a lot of people don't use, but it is a backport compatible, and it's very important in some of the places where you already have existing infrastructure to use this, and that's why they have included it. There is an RS-232 serial port programming as well, and Ethernet. Now what you notice is that what is missing is USB. This doesn't have a device USB port. It has a host USB port in the front, but not a device one. I have no idea why this has been omitted. I would have much preferred to have a USB port than, for example, the RS-232 one. But nonetheless, it's obviously connectable through the Ethernet, so you can upload and download files onto it and control it through the Ethernet. It's just surprising that USB has been omitted. Now, in terms of BNC connectors, you have a whole bunch of different functionality available here. For data synchronization, you have a symbol clock and 3 configurable event BNCs, which we might take a look at. For vector modulation, you have INQ input and INQ output. Unfortunately, the INQ input and output are all single-ended, and that's most likely because of the space constraint here. But you have to basically mean that if you have a differential system, you're going to have to terminate one end and just use the single-ended input. And they're all rated to plus or minus half a volt, which is also fairly standard. You have your time base in and out, as well as the analog modulation in and out. The fact that everything has an output, for example, the modulation port, can be really handy because it means that you can simultaneously use this as a reference transmitter and apply your own INQ signals to your own transmitter so that you can have a comparison. This is why sometimes I like to have differential INQ in and out, because a lot of designs use differential IQ for obviously all the advantages that differential signaling has, and having a single-ended one can sometimes be a little bit of a problem. But considering the footprint and the area it occupies, they've used all the area available for the BNC connectors and give you tons of functionality. So now we have to really take a look and see how the GUI performs and how the instrument performs in different applications. And here's the unit after it has booted up. It takes about 15 to 20 seconds to get to this point. And the menu system of this unit is really straightforward. And this is what I wanted to briefly show you. Pretty much all the settings are accessible through this setting menu. Here you have your RF, LF, modulation, AWGN, utility, and analogs directly accessible with the soft buttons at the bottom. You can also change the frequency and the amplitude, and the frequency of course goes from DC to 6 GHz, and the amplitude from 16.5 dBm to -110 dBm, which is a nice large dynamic range, allowing you to use it as a reference transmitter or to test receivers with different sensitivity and different linearities. The RF LF menu over here gives you the option to control the LF output, and this is where you can set its output power, its offsetting volts, and here you can also choose the PLL mode. So it has two PLL modes which will give you two different PLL phase noise profiles, and we will take a look at that, and it can be handy depending on what it is that you're testing. And the phase can be adjusted. The reference phase of this as a transmitter, for example, can be adjusted there in 360 degree modulus format, and that's by all the way down to 0.01 degree adjustment, which can be very handy if you're testing different types of receivers and you want to find out what the phase offset has, what kind of impact it has on your receiver. Now, under the modulation menu is where you have all the functionality of the vector modulation capability of this unit, which is the highlight of its functionality because it is equipped with a dual arbitrary waveform generator, and it can create double sideband and single sideband modulation and custom modulations if you were to upload your own data. Here, by selecting the modulation type and using the rotary knob, you can select, for example, under analog modulation, AM, FM, PM, and pulse, and you can go back, and if you go under vector modulation, this is where you have the arbitrary waveform generator capabilities. ASK, FSK, PSK, QAM, even CPM and VSB are of course all supported. Now if you go under presets, you have a whole set of different industry standard communication protocols and modulation formats which are defined in the manual of the unit, so they're fixed with a certain type of characteristic which you can use to immediately test a product which is supposed to work with one of these industry standard modulation and communication formats. So it supports a whole range including P25, GSM, CDMA, DECT, and so on, and obviously AM audio and FM audio for audio devices. So it's pretty straightforward and really handy to use. Now, if I were to go over here and, for example, select something like a vector modulation and go under QAM, then once we select that, then you get a little menu over here which describes the current settings of the QAM modulation, and you can change your constellation types exactly like this. You can have a custom one where you can download your own modulation type and modulation points and so on, which is quite nice, and it goes from 4 QAM all the way to 256 QAM. Now the source can be selected as being a PRBS, a particular pattern, or an external, and the external will then use the external INQ input. In that case, you can do whatever modulation you want, which is quite nice. And under custom, you can have also saved ones, which currently is all empty. You can set the filter, which would be the different types of filter. You can have a whole range, which is quite nice, including root raised cosine, which is the standard rectangular, which means basically nothing, and even a custom one you can download your own. So this is really handy because you can test a whole bunch of different characteristics of a receiver by changing the filter, for example, by embedding a type of filter that has noise outside of the band that you want, and see, for example, if your diplexer can take it out sufficiently, and so on. So it's very handy to be able to have a programmable type of filter over here. You can also change the symbol rate, which goes all the way up to 6 megasymbols per second, and the scale factor here you can change, which is just the scaling of the IQ signal and the PRBS length and so on, and we will take a look at all of that. So it's pretty nice and straightforward. Now on top of your modulation, you can add an AWGN type of noise, which is really handy because it will tell you what type of sensitivity your receiver can have to AWGN noise, and you can set the AWGN power as a reference to the transmit power. So if you have a specific SNR in mind, this is how you can emulate that SNR. Very handy, and you can add imperfections to the I and Q offsets, and we will take a look at that as well. Other than that, it's really nice and straightforward. Now, there's something that's missing from all of this, which I cannot find, and I don't think it's implemented, and that's multi-tone. It should have a multi-tone menu built in where you can generate a table of tones and you can turn individual tones on and off, and that would then get up converted directly to the RF, because a multi-tone generation is one of the most fundamental tests that you have to do on a receiver and on a transmitter, so you have to have that capability built in. Obviously, you can always download your own waveform and get whatever you want, but having it built into the unit directly is really important, and I'm sure that that's something that with the firmware upgrade they can add, and I will make sure to ask for that as well, because a multi-tone generation is extremely important. So it's currently not implemented, but I'm hoping that it will be coming. So now that you have a rough idea of what this menu system looks like and how easy it is to use, I want to do a couple of performance verification tests on it, and then an experiment where we actually use it in different modulation formats. So one of the very first things I want to measure is the output power of the synthesizer and see if it meets its specification. Now Tektronix boasts that this thing has a very accurate output power representation, and we can easily verify that. I'm going to be using an Agilent U2000A USB power sensor, which goes from -60 to 20 dBm. It's a really wide dynamic range unit, and it is fairly well calibrated, so we should be able to measure the power directly. And I've connected it right at the output RF connector, so the measurement plane is right at the connector. There are no losses because of cables or connectors or anything like that, so we should be measuring the raw power directly from the unit. I've set this to 1 GHz and 0 dBm, and the output is disabled. And you can see on the computer the USB power sensor software is running, and it's reporting -60 dBm, which is just a noise floor of the instrument. So just go ahead and enable the output, and here we are. And check it out, that's really good. 0.005 approximately, if I were to average the last digit, and you can see how nice and stable that power is. It is definitely meeting the specification at this frequency. I'm very happy with that. Let's go ahead and increase the power to the maximum and see if it meets its 16.5 dBm output power at 1 GHz. And that's easy to do. We can go crank it up all the way up to 16.5. There we go, 16.46, which is very close to 16.5. I'm pretty happy. You can see it's about 16.47 even. So it is very close to the maximum power it's supposed to be able to provide. So no complaints over there. But it's a little bit easier to meet this specification at 1 gig than it is to meet it at 6 gig. So let's go ahead and crank it up all the way to 6 gig. And actually, let me change the amplitude to 0 dBm. So we can go back to 0 dBm, and I can change the frequency here to 6 gig, and I'm going to go over the software here and change the frequency of operation here to 6 gig so the correct calibration coefficient can be loaded into the instrument. And here we go. We are reading at 6 GHz with a 0 dBm power just slightly under 0 dBm, and this tends to happen that the output power accuracy of synthesizers tends to be a little bit low at the higher output powers. Now if I go to amplitude over here, I can go ahead and crank this up all the way to 10, for example. So at 10 dBm, 9.95, you can see that it is very, very nicely stepping to 10 dBm as to be expected. And we can go to 15, and you can see 15 is now slightly over what it should be. And at 16, it doesn't meet quite the 16. So if I go to 16.5 dBm at the highest frequency, I'm actually a dBm short. Now I don't see an unlevel come up on the instrument itself, because I guess it's not detecting this to be a major problem, but normally you should see an unlevel come up telling you that, yeah, you're asking for 16.5, but you're not quite getting 16.5. But that's okay. This, yeah, again, it can happen. It's sometimes at the high end of the frequency of the synthesizers, you're not going to be able to get exactly what you're asking. But other than that, I think it's very nice and very accurate. We can also go on the low end. So let's go back to 0 dBm, like so, and you can see we're back to the value we were measuring before, and I can go down 10 dBm below, and it's -10.36. You can see it's doing a good job at tracking that output power by 10 dB at a time. Here's -20, exactly 10 dB drop, -30, very close to 10 dB drop, -40, again 10 dB, 50, and then once you hit -60, then you're just the noise of this instrument anyway, so you can't really rely on that very well. But I would say that it's very good. Again, at the very highest frequency, it's difficult to meet exactly the precise power coming out, but it's pretty close. I should say I'm fairly happy with this. And if the unlevel would have come on at the 6 gig highest frequency, so when I select 16.5 dBm here, it would be nice to see an unlevel, but I don't actually quite see it show up. I don't think it's generating an error. If I go under error log, it's just telling me a bunch of illegal values that I tried to enter, but there's no unlevel in the list here. But nonetheless, I would say that it's pretty good. Very close representation of the actual power. And just to show you as a comparison to know that these things actually are quite normal, here's the Keysight EXG, which is a considerably more expensive unit, and here at 6 GHz set to 0 dBm, you can see I'm reading actually a little bit over. So Keysight tends to be a bit more aggressive with their powers. They tend to be over what they're supposed to be, slightly at the end of their frequency span. So it's normal that this is the case, but just to show you that it is in fact true, I can go ahead and change the frequency to 1 GHz, and I can go over here and set this to 1 GHz, and you can see that it's just slightly over the 0 dBm that I'm asking for, but it's closer. So let's go back to 6 gig over here, and I'm going to go over the frequency here, change this back to 6 GHz, and under the amplitude I can go ahead and crank the amplitude back up, So this unit is actually capable to going to all the way up to 19 dBm as the maximum. So there you go. So we are sitting there, it's at 19 dBm. So we're just again a little bit over. Now if I go, as soon as I start going to 19 and a half, I'm still meeting it against this 0.2 dBm higher. Now once I hit 19.7 or so, there you go, 19.8. Now it's still over, but it thinks that it can't meet the 19.8, so I'm getting an unlevel error over here. So now if I continue increasing this and I tell it 20.8, yeah, it's gonna say sorry, it's on level. So you can't rely on that. So this error is fairly common to show up on synthesizer, especially at the higher end, when you're not able to meet the power, but you're actually still able to set the number. And that's something that probably they can fix with the firmware. They can add to that. But as an example, so we can see a comparison here. So let's take a look at some of the signals directly on the spectrum analyzer. So I have connected the Tektronix TSG4106A directly to a Keysight EXA signal analyzer. By the way, I've done a full review of this EXA. It's more than 1.5 hours long. It has lots of really interesting experiments in it. So I highly recommend that you take a look at it as well. So here the signal is at 1 gigahertz, and you can see I've set it to 0 dBm and 1 gigahertz, and we can clearly see the spectrum over here with our fundamental tone all the way up here and a few of the harmonics here, and all the harmonics are 40 dB below the fundamental, which is great. So at this frequency it has excellent harmonic rejection. Now, as with any synthesizer that relies on multiplication, and they all do essentially, there's going to be some frequencies where your harmonic distortion is going to be worse because you're at the boundaries of the multiplications. So this is going to have the same issue. So let's find out what the worst frequency for that is. And if I continue increasing the frequency, you can see the behavior of the harmonics will change. Some of them will go up, some of them will come down. And for example, here's a clear point where we have some jump between where the multiplications happen. And if I continue up higher and higher, at around 3 gigahertz, right here is where I have the worst harmonic rejection. So my fundamental is at about 0 and the second harmonic is at minus 20. So I have about 20 dB rejection, which is not bad. And in most cases that's sufficient for the application you're targeting. Only in some situations when you have really broadband circuits can this be an issue. Most of the time the circuit you're interested in has some harmonic rejection on its own anyway. But nonetheless, it has a quite nice pure tone at the worst case of even 3 gigahertz. If I continue up, you can see that it will again improve quite significantly. And if I go all the way up to maximum frequency, which is 6 gigahertz, I have excellent rejection. This is a very pure and clean 6 gigahertz tone. So it's all nice and great. So let's go back down to around 2.4 gigahertz, which is within the ISM band. This is probably where most of the people will be interested in using it. And let's take a look at the signal a little bit closer. So the center frequency is here, 2.4 gigahertz, and let's go ahead and change the span to a much smaller signal, let's say around 1 megahertz. And I'm going to change the resolution bandwidth as well so we can get a better noise floor there. And I can go ahead and enable a modulation. So let's say I want to do some basic modulation, and here I have what I have. I have an FM modulated signal, and the source of the FM modulation is sinusoid, and I have a rate of 50 kilohertz and a deviation of 10 kilohertz. So let's go ahead and turn it on, and we see very classic tones that are around the carrier, and this is defined by the Bessel function because this is a sinusoidal modulated FM signal sitting on top of 2.4 gigahertz. And if I go ahead and change the deviation, you will see the harmonics around the main tone change, and eventually the carrier begins to be extinguished. And this is pretty normal. If you study the Bessel function behavior of an FM modulated signal, you will see this, and it does quite a nice job at generating FM signals. Now this is obviously pretty straightforward. What I really want to see is this complex modulation based on the vector modulator that's built into it, and in order to do that we have to actually do some demodulation, and we will do that as well. So let's go ahead and turn the modulation off for a second and take a look at the phase noise. I want to show you the different phase noise profile this instrument actually has. So in order to do that, we're going to go under mode, and we're going to change the mode to, where's my phase noise measurement? There it is. Into a phase noise analyzer, and then the carrier frequency here has to be changed to 2.4 gigahertz. There it is. And I'm going to change the measurement to a log plot, and we're going to stop all the way at 100 megahertz. And we're going to go in a continuous measurement. There it is. So we can see our phase noise measurement here. Now the phase noise of this synthesizer under some situations is reasonably close to the EXA. So there's going to be some additional phase noise from the EXA being on top of the phase noise of this, and this is normal. Under some situations this can happen. Keysight does have other spectrum analyzers with far greater phase noise capability, which then can really accurately measure the phase noise of this unit. So what I really am interested to show you is how the phase noise profile actually changes. So take a look at this region of the graph right over here. Right now we are in PLL mode 1, and I can change that, as I showed you before, under settings and under RFLF. You can see I'm in PLL mode 1. And if you pay close attention to this region right here, I'm going to change it to PLL mode 2, and you can see how the phase noise profile changes. Let's change it back. You can see that there is a small difference between these transitional points. So they're changing the PLL bandwidth internally. You may ask, why are they bothering with that? Well, it actually can be really important for you to study the effect of your own PLL if you're using this as a reference. This allows you to study how the different PLL profile of a reference can be interpreted and can be shaped by the PLL that you have designed yourself. So it's very cool to have this, and all high-end synthesizers do have this capability to give you at least a few different PLL modes, and that is good to see that this guy also supports that. Now that we've seen some basics, let's go ahead and do a quick demodulation of a QAM signal that this can generate directly on the EXA, and then we will connect it to our own down converter so we can see the baseband signal coming out, and that will be our main wireless experiment. So let's look at some more advanced modulation. Here I've set the unit to 3 dBm, which is the highest output power it allows under this complex modulation, and the center frequency is still at 2.4 GHz within the ISM band. Now the modulation type is 256 QAM, and I'm using a PRBS 15 as a seed, which is a sufficiently scrambled input data there, and I'm using a root raised cosine for the pulse shaping with a coefficient of 0.35. Now the data rate here is 6 megasymbols per second, which is also the highest that this unit supports. At 256 QAM, we're dealing with 48 megabit per second, which is the highest throughput that this unit also supports. So I can go ahead and enable the modulation. And once enable it, you can very clearly see on the spectrum analyzer the shape of the modulated signal. Very classic, looks quite nice. I don't see a lot of power on the adjacent channels when we'll measure that. I do see some tones appearing here, and you can see that these two tones are most likely generated by the DAC. They're unwanted. They are in the adjacent channels, and they could be an issue under some circumstances, but they are sufficiently low in terms of their power that in 99.9% of the situations you will not see this causing any problem at all. And in fact, we will measure the adjacent channel power, and we will see that it's not interfering. So we can go ahead and change the mode and go into the VSA software, and we're going to have to acquire that. Where are you? There we go. And now you can see the demodulated signal. I'm going to refocus the camera so we can take a closer look at the quality of this modulated signal. And here we are, we can take a closer look at the quality of this modulation. Here's our constellation over here, looks very nice as you can clearly see. And at the bottom we have the spectrum. And I'm measuring the total power of the modulated signal, and it's about 3.5 dBm. I changed the scaling factor to 2 on the instrument to get about 3 dBm, which is quite good. And you can see the adjacent channel powers that are at minus 56 dB lower than the main channel, which is again quite high, and for most applications it's not a problem. So the tones that we saw do not seem to be contributing very significantly to adjacent channel powers, and it doesn't really cause any problems. And now if you look at the quality of the EVM that we're getting an EVM of about 1.3% RMS, which is also quite good, and the SNR is 37 dB. Now it's important to note whether this SNR limitation is due to channel linear response or is it due to a noise SNR limitation, and we can investigate that by enabling equalization on this. Let's go ahead and enable equalization, and when I do that I will get an improvement of quite a significant improvement in the EVM. I'm down now to about 0.6% RMS, and now my SNR is now 43 dB, which is quite a bit higher. This means that most of the limitation was due to a channel linear response and can be corrected with equalization, which is great because you don't want to have an SNR limitation due to noise on your reference transmitter. So that's one of the advantages of this unit, that it has quite a good EVM performance, especially once corrections are applied. So now that we have this information, we can go ahead and try and characterize a reference receiver now by using this as our transmitter, and get our IQ data out and put it on the oscilloscope and actually see demodulation take effect from our own receiver chipset. And then we can look at the SNR of the unit because remember I spoke about the fact that this unit can add artificial SNR onto the signal, which can be quite handy, and we will see that. And one last thing I want to measure is the capability of the unit to perform very high bandwidth modulation, because this is limited to 6 megasymbols per second, but the unit boasts about the fact that it can accept IQ inputs with a much larger bandwidth. So I'm interested to see the image rejection under broadband input. So we'll take a look at that also. So for our experiment, I'm going to be using this Analog Devices ADRF6807. This is a full IQ demodulator with a built-in PLL. It's actually a fractional PLL. We're going to be using it in an integer mode. But nonetheless, it has a built-in synthesizer as well. So the reference for the synthesizer is coming over here. I'm going to be using a 25 megahertz reference, and the RF is going to come from the Tektronix vector generator right over here, and the I and Q outputs, which you can see here, I've terminated the Q output into 50 ohms, and the I output is going directly onto the EXA signal analyzer. Now I could connect these two to an oscilloscope and use it as a direct conversion 0IF, but in order to simplify the setup, I'm going to use the spectrum analyzer and use this in a heterodyne mode, but the IF is going to be pretty close to DC anyway, so I'm going to use a 25 megahertz IF. So it's not too bad. It's going to be very representative of its performance nonetheless. Everything is connected together. This is programmed through the USB port. Two power supplies are connected. So let me show you the components of this setup. As I mentioned, the RF signal is going to come from our Tektronix vector generator. The spectrum analyzer at the top is going to be used to look at the IF. I'm going to use the Keysight EXG to generate my reference. You can see set to 25 megahertz already. I'm going to use two Agilent power supplies for the 3.3 and the 5 volt supply required to run the board. And finally, I'm going to use the application that is running on the computer over here to configure the IQ demodulator to a 900 megahertz carrier, which is what is going to be used right now. Now, as I mentioned, because we're using this in a heterodyne configuration, you can see that I have my carrier set to 925 megahertz. That's going to put our IF at 25 megahertz. Now, if I go ahead and enable this, we should be able to see directly on our instrument. Right now, this is set to a center frequency of 25 megahertz. I'm going to enable the RF, and voila, there it is. This is our down converter signal. You can see it works quite nice because the PLL inside the down converter is already locked to a 900 megahertz. So if I disable the RF modulation, you can see that we're going to get the tone back at 25 megahertz. This verifies everything is working, and there is our modulated signal. So now I actually am using the vector generator as my reference transmitter, and my demodulator is converting it back to IF. So I'm interested in finding out the performance of the SNR of this down converter chip as a function of the input power coming from the Tektronix. This is a classic test. Unfortunately, as I said, this doesn't have multi-tone built into it. Otherwise, we could actually do an OIP3 measurement. This is why it's so important to have this particular unit embedded with a two-tone or multi-tone generator, and I'm sure this is something they're going to add because this is a very early firmware version of this, so I'm going to look forward to that. So let's go ahead again to zoom over here so we can take a look at the demodulated signal closely and see its performance versus input power. So let's go ahead back to the VSA software to take a look at the constellation. And there we go, and I have to minimize and maximize this because of some unusual bug in here. There we go, now we can see the constellation once again, and we can see some signs of phase noise due to the smearing of the points on the outer corners of the constellation, and that's to be expected because we have the internal PLL of the demodulator active, and that's going to have some added phase noise. All the signals here are uncorrelated, so we don't have any phase noise cancellation. So having said that, we can see that the SNR has degraded to about 35 dB. The input signal power into the demodulator right now is at minus 10 dBm. So if I were to go ahead and decrease that, eventually I'm going to reach a point where the noise of the demodulator is going to become more dominant than the other imperfections in this constellation, and we're going to see the SNR degrade. So let's go ahead and try that. So right now I'm sitting at minus 10 dBm. Then we're going to go to minus 20 dBm. Now it's minus 30 dBm, so we still look pretty good. Minus 40 dBm. Let me go ahead and re-auto range this guy. There we go. So at minus 40 dBm, we're beginning to see some loss in the SNR. So let's go now one by one. Let's go to minus 45. There you go. You can see now we are seeing degradation. We are no longer actually even seeing the phase noise issue anymore. We are now directly reaching below the noise floor of the demodulator chipset itself. And if I continue to go down, you can see now I'm sitting at minus 50 dBm, and now it's becoming quite poor now, having a little bit of a difficulty locking to it. Let me auto scale, make sure we're sitting at a good reference. There you go. You can see now our SNR is about 29 dB or so, and there's a bit of a problem locking into it. I can go ahead and make some changes, but anyway, it's sufficient to get the point across. So you can see how by reducing the power, we can detect the noise of the demodulator itself, but we can actually do something quite interesting as well. Let's go back to let's say minus 10 dBm like before, and let me auto range that so that we're not limited by the linearity of the instrument. There we go. So now what I can do is I can go over here and actually play around with a built-in AWGN generator of this vector modulator itself. Remember I talked about that briefly, and if I go under settings, if I go under AWGN, I can actually turn on my own noise from this vector generator and see its impact directly on that unit. So let's go ahead and do that. I can go ahead, right now the noise is set to minus 50 dBm, so minus 50 dBm lower than the power of the signal, and I'm going to go ahead and enable that by saying add it. And I'm going to come over here. Actually, you probably can see it at the same time. You see that I don't see much of an effect yet, but if I go ahead and change the power of the noise from minus 50 to minus 40, I am now beginning to see exactly the problem. So without having to attenuate this, by adding my own noise directly to the up converter, I can emulate the effect of the SNR degradation that you might see at the input of the receiver. And this is really helpful because it allows you to investigate how much added noise can you have directly from the transmitter, from the environment, before your receiver becomes the limiting factor. So if the noise is really small, let's say it's sitting at minus 60, it has no effect because we're already below the noise of the demodulator itself. But once we hit minus 40, we're beginning to now be greater than noise of the demodulator, and that can easily be detected by the software. That's very helpful and very handy function to build in here that I wanted to show you. So now the only thing left here is to take a look at the capability of this unit to accept external IQ signals, because the internal one can only do 6 megasymbols per second for QAM constellation. So its bandwidth is rather limited. But if I were to apply externally, I can use this as an upconvert mixer, and I can do my own single sideband signal. So let's go and see what the broadband image rejection of this looks like, and then that will be our last experiment. So in order to investigate the capability of this unit for broadband IQ modulation, I'm going to be using here this Agilent N6038 to generate IQ signals all the way up to 200 megahertz per side. And sorry about holding the camera in my hand. I just want to show you that I'm using these cables then to come directly and of course then feed into the IQ modulated input from the back. And this allows me to generate very broadband IQ signals, and then we can see how well this instrument handles really high frequency inputs at the back and see what happens to the output. So then we can now move on to the spectrum analyzer and look at the output. So what kind of broadband IQ signal I'm generating? Well, you can see it all the way up there. If you zoom in, all the way there, and there it is. So you can see I'm using the software there. I'm generating 200 tones starting from 1 megahertz all the way up to 200 megahertz, and that's going to occupy a full 200 megahertz of single sideband signal that's going to come out, and we can see some performance limitation all the way up to 200 megahertz. I'm very curious what the output of the synthesizer would actually look like. So I have the synthesizer right here, and you can see that I'm setting it to 2.4 gigahertz, again some frequency which would be of interest to a lot of people. And right now the modulation is disabled, as you can see. It's not lit over there. And if I go all the way to my spectrum analyzer over here, which is somewhat crooked right now, if you look at it, you can see the tone very clearly. Now that tone obviously has no modulation on it, it's just the main carrier sitting at 2.4 gigahertz. Now I can go ahead and enable the modulation and check it out. Here it is, and it has a very classic characteristic. The reason it looks so solid is because there are 200 tones very, very closely packed to each other. And now you can see some basic performance there. For example, you can see that near the carrier, the image rejection is very, very good, and to be expected. We're talking about 10, 20, 30, almost 40 dB of image rejections. Essentially ideal as far as for practical purposes there. But as you go away from the carrier, you can see that the image rejection begins to degrade, and that's also to be expected because you're moving away from where the signal is optimized. And I can use my marker to find out what happens toward the edges. Let's move the marker all the way to the end over here, and you can clearly see, by the way, that this is indeed 200 megahertz, because now we're sitting at 2.6 gigahertz and carrier is 2.4. I'm going to make a delta marker. I'm going to move that point all the way back over here. At the very, very edge of 200 megahertz, we have an image rejection of about 18, 19 dB, which is pretty good considering how broad spectrum this modulation actually is. So now we can also try this at a different carrier to see if the performance changes. So let's try somewhere a little bit higher at 5 gigahertz, and just to have for completion. And here we are sitting at 5 gigahertz. And it's a couple of interesting things to note. The signal is being actually applied to the IQ input at the back of the unit, even though the modulation port is disabled. So the signal is always present. It's blasting it with, you know, half a volt of swing per I and Q port, and you can see there is some leakage coming through over here because they can't completely isolate it even when we turn the modulation off, which is not a problem. We're talking about 90 dB down here, so it's not really an issue. Now I'm going to go ahead and enable the modulation. And check it out, the response looks very, very similar. It has a, you know, similar performance, obviously a little bit degraded, and you can clearly see that the shape of this has changed a little bit because the bandwidth of the modulated signal is a little bit different. So the up converter doesn't have as much of a flat response at around 5 gigahertz, and it does at 2.4 gigahertz. But it's really not an issue because these type of things can be compensated with equalization. But I'm very happy to see such a broadband modulation capability directly built into the unit. Obviously you can go even more than that, but then your image rejection is going to continue to degrade. You may not care about that depending on the application, but it's very cool, and you can see that this is a really tough test to put this instrument through, and I'm glad to see that it performs quite nicely. And one last thing I wanted to discuss very briefly is the software that comes with the TSG. Now I'm not going to spend so much time on this because if you look at this, this is actually on version 0.1 beta. So it's just something they've put together to get some initial connectivity going on with the unit, but it's not really completely finished and it lacks quite a bit of functionality. Obviously you can connect over GPIO or a Visa port, and a Visa port unfortunately crashes on my computer. And I think I have to probably run this as an administrator if I'm not mistaken. We can try that and see if that would help the situation. No, it still crashes. So unfortunately I tried a whole bunch of different things to get it to work and I couldn't, and it continuously does the same thing. But not to worry, we can still take a look and see what we can do with it. And one of its main functionality is that you can create new constellations or analog waveforms or different types of vector waveforms, and based on symbols or IQ data, and then, you know, generate them and fill in these blanks or load them from a file and then download them into the unit. But it's quite rudimentary. It doesn't have a lot of functionality built into it. And if I were to criticize this instrument, this would probably be my biggest criticism, that there is a tremendous amount of untapped potential here which can be taken advantage of by this software. If this software were to be developed in order for it to be able to generate the types of waveforms you would normally want to generate in a test environment, like multi-tones and missing tones and different constellations very quickly and easily, and show you the waveform and show you all the parameters that you can enter directly from the software, that would already make this a far more useful unit and can do things much, much faster. Right now, if I want to do that, I'm going to have to spend quite a bit of my own time to generate the data. Some people already have the ecosystem for this and they can generate this data very quickly, but you know, it would be very helpful if they were to develop this, and I'm sure that with all the expertise they have, it would be quite easy for them. So that would be my biggest recommendation, to really cook this software up and make a nice version 1.0 that has a lot of features, and I'm sure that they're going to do that. That's why I don't want to spend too much time on it, because it's still a beta, but know that it is available. You could use it potentially to download different types of IQ data directly onto the unit. And there you have it, a really close look at the Tektronix TSG 4106A. I'm pretty happy with it, and as I mentioned, I have a few criticism here and there, and there's a lot of potential that I hope to see from Tektronix being taken advantage of, especially on the software side. And I hope that you enjoyed this close look at this. And as you know, these episodes take quite a bit of time to produce, especially because there's a lot of technical detail that it has to be done quite correctly to really demonstrate the instrument's capability. So if you like the video, let me know, give it a thumbs up, and more importantly, let Tektronix know that you enjoy these videos, and then if you make any purchases based on that, let them know. I don't get any share of the sales or anything like that. This is just so that I can have a good rapport with these manufacturers and be able to bring you cool reviews like this into the future. So until next time.